So we're going to take an example of how we can use parameterization to calculate the work when we move along a different kind of path that is not a straight line segment along x and y. So in this example, I have sketched a Cartesian coordinate system x and y. We have an object at this position here. We're going to move that object to a new position, so we're doing some work, but we're doing that along a half circle. That circle has a radius r, so at some point when we are here, for example, we can specify the position through the radius of that half circle. Imagine the full circle with the radius r, and we can specify by the angle theta. So this is an example of polar coordinates, where we specify the location as a radius, which in this case is constant, and the angle theta, which is the one that is varying. So that's our path L. Okay. So we're going to calculate the work done. In this case, the force is given as a function of x and y. And I'm going to have my notes here to see what it was. It was the force we had before in the other examples as well. So it's 5 x, y along the x direction plus y squared in the y direction. Okay, so that's our force. The work done is the line integral along this line or this curve L. The force dotted with the infinitesimal line segments. Again, we took this line and broke into a bunch of tiny little elements. There will be the work along each tiny little element, and we just add them up, sum them up in form of the integral. But now we're going to use the parameterization, because doing this with x and y becomes more difficult. So we're going to go into the parameterization and say this work can be written as the integral of f of x, which can be written as, so this is should be not a, which can be written as a function of some parameterization variable s, then the derivative of x with respect to that parameterization variable s times the differential of s. So that s is some geometrical parameter that can be used to describe the path and the force as well. Do the same thing for the y component. Keep in mind we're only working in the two-dimensional plane here. Okay, so this looks really ugly, but this is the general approach. Now we're going to see how we're actually applying it. So in this case here, what parameter is it that we can really use to describe the location, the position of this object as we move along the house? So we can say, well, that's going to be our radius r. Well, that's a constant. So it's not really giving us much additional information. What really matters here is the angle theta. So in this case, we will say S, that parameterization parameter that describes something about the location of this object here, or the geometrical property, is really our angle theta. So now let's write it down again here. I'm not going to write this function of s, I'm just going to leave that as is. And then we have dx, but now it's dx d theta, and s is theta, so it's the differential of theta, plus f of y dy d theta multiplied by the differential of theta. So we recognize that theta is a good parameter to parameterize the path. We have not parameterized the force yet. However, if we were to draw the force here, we could always split it into components, right? But we do know something about these geometrical components here. Remember, from this definition here, we had to have information of the x component, or x position as a function of this parameterization variable, and the y position as well. So this becomes x as a function of theta and y as a function of theta. But from trigonometry, we know that x can be written as the radius that's the projection down the x-axis, that's the coordinate, right? R is a constant, that's the radius. Cosine theta, and y is our r sine theta. So we now have written our x and y components or positions as, not x and y components, but the x and y positions as a function of theta, which is exactly what we needed to do. So let's try and see what happens here then. Let's try and plug it in. We still have the function, this component of the force of x. But let's give it as x and y. So it's 5 times x. Well, x is r cosine theta. We parameterized everywhere where we had x and y. We now have to replace these x and y's with the functions that depend on that parameterization parameter. Y is r sine theta, so we plug that in there. Then we have the x d theta. Well, we know the function, we know x and how it depends on theta. So we could take the derivative of x with respect to theta. They gave us a negative r sine theta. And then we multiply it by the differential. Okay. So that was our first term here. Yes, it's not pretty, but it does allow us to actually solve the integral. Now take the y component. That's going to be 5 multiplied by y squared. Well, y squared is going to be r squared sine theta squared. And then we have, here we go, dy d theta, which is going to be r cosine theta. And then we multiplying by the differential of theta, and then close the bracket. Now what about the integration? We're not going from x equals 0 to 1 or anything like that. We're now integrating with respect to d theta. So when we start in this point here, theta 1 is equal to 0. We go all the way around to the other side here. That is theta 2, or the final endpoint, equal to pi. So we're integrating over this parameterization variable theta from theta equals 0 to theta equals pi, or 180 degrees. So let's try and write this here out. This is theta equals 0, theta equals pi. And then we see, let's say we have a 5. We have r cosine theta. And then we have r sine theta multiplied by negative r sine theta. So that's r squared, negative r squared sine theta squared. We have d theta, but we also d theta here, so we can pull this d theta outside this bracket. So plus, second term here we have 5. Then we have, I'm going to move this r cosine theta in here. The second factor here, the third factor, is r squared sine squared theta in the bracket, and then we have d theta. We integrate with respect to theta. Lo and behold, we see these two terms here are identical, but this one has a negative sign, so all this adds up to 0. Whoopty. That is great. That was pure luck on my part, or maybe because I chose this example so I didn't have to go through lengthy calculations here. But this is the approach. You find you have this curve to be given a problem. You know something about the force, but in terms of the Cartesian coordinates x and y, the problem is not suitable to solve in terms of integrating with respect to x or integrating with respect to y. So we parameterize it. We find a parameter, and of course in physics too, it will be pretty obvious what that parameter will be. In most cases, it will be polar coordinates. We're using theta as the parameterization variable. We define our x and y positions in terms of this parameterization variable. We get these functions. Then we can calculate these factors in the integrands here, these derivatives. This is, if you have taken Calc 3, you can try and compare that to what you call the Jacobian, or the determinant of the Jacobian, which is more exact. And that tells us exactly what those kind of values or functions would be. We replace in the expression for the force with x and y's, we replace that with the parameterization of x and y. And then we have an integral in terms of the parameterization variable, which in this case is theta. Sometimes the integral is nice, like in this case it's just 0. Other times it's not so nice, but it is possible to solve it, which is the key.